Hello and welcome back to this video series about the Intermediate Math League of Eastern Massachusetts. Today we're continuing on with the number theory section for Me 3, where we'll be talking about bases. So let's get right into it. So the only thing we have to talk about today are bases. Now before we get into converting from base to base and doing operations in different bases, we really have to understand what a base is, because that's really going to help us. Now you'll notice at the top of the slide is labeled Bases Explanation Part 1. And the reason for that is because I'm actually going to be explaining what bases are in two different ways. Now this first way, which is on this slide, is the one that makes more sense to me personally, but I know the second way that I explain it makes more sense to some other people as well. And since bases are really complicated, I chose to include both explanations in this video. So here's the first explanation of how bases work. And if this one isn't really making sense to you, you could probably skip ahead to the second explanation where I'm explaining it a different way. So a base is basically a number that represents how many one-digit numbers there are in a number system. Now, we operate in what's called base 10. Everything that I've ever taught you in any video has been in base 10. And I'm guessing that all the math that you ever have done has been in base 10. So first, let's understand what base 10 means, because that's going to be the one that makes the most sense to you. So down here I have a number. This number is 1010.1, and it's written in base 10. So what bases change about numbers in different bases are the place values. I'm sure you know what a place value is, so we're going to start nice and simple with this number here, this 0. So this 0 is in what we call the ones place, right? It represents that we have 0 ones in this number, 1010.1. So if I label that, that's the ones place. And I'll get to what else I wrote in a sec. Now, if we label all the other place values in base 10, they're the tens place, the 100s place, the 1000s place, and the 10th place, right? So if I label those all, now we have the labels for all of them. So basically what this number represents is you have 1000, because there's a 1 in the 1000s place. So you have 1000, and then you don't have any 100s because there's a 0 in the 100s place. Then plus, you have 110, so 1 times 10. You have 0 in the ones place, right? Because there's a 0 here, so you have 0 ones. And then you have a 1 in the 10th place. So plus, oops, that wasn't a good plus. Okay, so plus 0.1 times 1. So what this number represents is you have 1/1000, 1/10, and 1/10th. And that's why you get 1010.1. So that's what this number represents in base 10. But you might be wondering, and this is what bases have to do with, why we call this the 10th place. Why isn't this the 50s place? Or why isn't it the 12th place or the 9th place? And why is this one the 1000s place instead of the 10,000s place or the 1020s place, for example? And then why is this one the 110s place or 110th place? Why isn't it like the 12th place or something like that? That's because we're operating in base 10. So the values of these place values get determined by what base you're in. The reason why is because the ones place, and we're starting with the ones place because this is the most simple one, is 10 to the power of 0. The next place value, the tens place, is 10 to the power of 1. 10 equals 10 to the power of 1. The next place value, the 100s place, is the 10 to the power of 2's place, because 10 to the power of 2 is 100. And then this next place value is 10 to the power of 3's place. And I accidentally wrote 100. I meant to write 1000 here, right? So 1000 is equal to 10 to the power of 3, which is why we call this the 1000th place and not the 1010's place or something, because no other number is 10 to the power of 3. And similarly, we have the 10th place because 1/10 is equal to 10 to the power of -1, right? So 10 to the power of 0 is 1. Then we go to 10 to the power of -1 for a point after the decimal. And 10 to the power of -1 equals 1 over 10 to the power of 1. This is how negative exponents work. It's just 1 over, and then whatever exponent you have, but now positive. So for example, if I 10 to the power of -3, that's equal to 1 over 10 to the power of 3. So 10 to the power of -1 equals 1 over 10 to the power of 1. And since 10 to the power of 1 is 10, that's 1/10. So 10 to the negative 1 equals 1/10. So that's why we have these place values equal to what they are in base 10. So therefore, what if we switch the base? What if we're operating in base 2, for example? Well, now the values of these place values actually change, and everything that we have up here goes away. So what these represent now in base 2 is the 2 to the power of 0's place, the 2 to the power of 1's place, the 2 to the power of 2's place, the 2 to the power of 3's place, and yes, this one represents the 2 to the power of negative 1's place. And so if we actually simplified all these, this is still the 1's place because 2 to the power of 0 is 1. So it represents that in base 2, you have 0 1's. This one is not the 10's place anymore. It's the 2's place because 2 to the power of 1 is 2. Remember, in base 10, it was 10 to the power of 1 here, which is 10, which is why in base 10, we call it the 10's place. In base 2, we call it the 2's place because 2 to the power of 1 is 2. And this represents that you have 1, 2. Now this is the 2 to the power of 2's place, or in base 2, it's the 4's place. Remember, in base 10, this is the 100's place because it was 10 to the power of 2. 10 to the power of 2 equals 100. But now we're operating in base 2, so we're no longer doing 10 to the power of anything. We're doing 2 to the power of something. And 2 to the power of 2 is 4, which makes this the 4's place. And then this is the 8's place for the same reason, because it's 2 to the power of 3, and 2 to the power of 3 is 8. So this is the 8's place, and it represents that you have 1 8 in this base 2 number. And then this one is probably the most difficult one to understand out of these. This is the 2 to the power of negative 1's place, or the 0.5's place, the 1/2's place. And the reason it's the 1/2's place is because if you remember, what the negative means in the exponent is you have 1 over and then the positive exponent. So 2 to the power of negative 1 is 1 over 2 to the power of 1. 2 to the power of 1 is 2, so 1 over 2 is 0.5, or 1 over 2 is 1/2. So this represents the 0.5's place, and you have 1.5. So in base 2, this number represents 1 times 8 plus 1 times 4, sorry, no, not 1 times 4, because we have a 0 in the 4's place. Sorry, 1 times 2 plus 1 times 0.5. And this is what changes from base to base, your values of the place values, or how the values of the place values are calculated, right? In base 10, the place values were calculated by 10 to the power of something. In base 2, they're calculated as 2 to the power of something. If I were in base 5, for example, then this would be the 5 to the power of 0's place. This would be the 5 to the power of 1's place, then the 5 to the 2, the 5 to the 3, and this would be the 5 to the negative 1's place. So that's what these numbers represent in different bases, and this is what changes from base to base. All right, so now I'm going to be attempting to explain bases in a different way. So this is where the definition that I had as for bases comes more into play, right? Earlier I defined a base as a number that represents how many one-digit numbers there are in a system, or in a number system. In the first explanation I gave didn't really fit with that definition because this definition tends to make more sense if I had to use just one for a base. So let me explain what bases mean according to this definition. And for that, we need to learn about counting, and specifically how we count in different bases, right? It may seem pretty primitive, but if we're just counting normally in base 10, because everything we've done in base 10, we count 0, and we're going to be starting at 0 for the purposes of explanation, even though you normally start at 1. So we're starting with 0, and then we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And say we're counting all the way up to 100. Eventually, we'll get to 98, 99, 100. That's pretty simple for all of us to understand, right? Learning to count is probably one of the first things that you do. But in order to understand what bases are, we need to break down how we count in different bases. So in base 10, these are all the one-digit numbers, right? You have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the only one-digit numbers that you have in base 10. And every single number you can possibly think of is made of these one-digit numbers. For example, 12 is made of a 1 and a 2. 98 is made of a 9 and an 8. 1,243 would be made of a 1, 2, 4, and 3. And you don't have any other one-digit numbers in base 10. Now, it's called base 10 because specifically in base 10, you have 10 one-digit numbers. That's what a base means. Remember, it's a number that represents how many one-digit numbers there are in a number system. And if you counted how many one-digit numbers you have in base 10, you have 0, 1, 2, 3, and 4. That's 5 total. Then 5, 6, 7, 8, and 9. And that's 10 total one-digit numbers in base 10. So this is what changes from base to base. So say I was counting in base 5, for example. Then theoretically in base 5, we should have 5 one-digit numbers. And that's actually exactly what we have. In base 5, if we were to count starting at 0, because 0 is our first one-digit number, we would count 0, 1, 2, 3, 4, and then we can't have another one-digit number, right? The number 5 doesn't exist in base 5 because we're only allowed to have 5 one-digit numbers, and we already reached that limit. 0, 1, 2, 3, and 4 gets us to 5 one-digit numbers. So since 5 isn't a number in base 5, we go directly to the next number, which is 10. So we go 10, 11, 12, 13. And then eventually, if we're trying to get to 100 in base 5, we get to 43, 44. And what would come after 44 is 45 typically in base 10. But remember, 5 doesn't exist in base 5, and neither does 6, 7, 8, or 9, because that's too many one-digit numbers to exist. We only have 5 one-digit numbers in base 5. So therefore, we're out of 2-digit numbers that we can create. So we have to move to our 3-digit number. So after 44 in base 5 comes 100. And I actually have here highlighted the one-digit numbers in base 5. This is what changes from base to base. You can only have as many one-digit numbers as you have the base number. So if we were in base 9, for example, then the one-digit numbers that we'd have would be 0, 1, 2, 3, and 4. That's the first 5 of them. Then we'd also have 5, 6, 7, and 8. But we wouldn't have the number 9 in base 9 because we already have 9 one-digit numbers, because these are 9 one-digit numbers total, right? And that's what changes from base to base. So if we're counting in base 9, it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, because we don't have 19 because that has a 9 in it. And when we got to the number 88, like in 100, how we get to 99, since there are no more one-digit numbers we can use, since we got to 99, which is the highest 2-digit number that can be created, we go to 100. In base 9, 88 is the highest 2-digit number that can be created because it's created only out of 8s. And since there's no higher one-digit number that you can create this number out, or one-digit number that you can use to create this number, we have to go to 100. So in base 9, 100 is right after 88. So yes, in any base, the base is the number that represents how many one-digit numbers there are in that number system. All right, so now that we hopefully know what bases are, we need to talk about how to convert from base to base. Because yes, you can convert numbers from different bases to another base. And specifically, we're going to start with converting from some base to base 10. So in order to convert something, a number in some base to base 10, you have to understand what the place values represent. This is how you convert. You have to use the place values, which is why I included the place value explanation as the first explanation, because knowing that one really helps you understand how to convert to base 10 a little bit more than the second explanation. So let's get into that. So in base x, the place values of a number are basically x to the power of 0 in this place, right before the decimal point. This is x to the power of 0 place. Then the next one would be the x to the power of 1's place. This one would be the x to the power of 2's place. This is the x to the power of 3's place, x to the power of 4's place here, and so on. And then in this direction, to the right, you go to the negatives. This would be the x to the power of the negative 1's place. And the next one would be the x to the power of negative 2's, and so on. And just to make sure you got this, for instance, if we had base 10, so x would be 10, because we're in base 10, then this would be the 10 to the power of 0's place, which is the 1's place. This would be the 10 to the power of 1's place, which would be the 10's place. This 3 would be in the 10 to the power of 2's place, or the 100's place. And the 6 would be in the 10 to the power of negative 1's place, or the 1/10th place. So in base 4, for example, then, we have the 4 to the power of 0, 4 to the power of 1, 4 to the power of 2, 3, 4, and negative ones place as well. If you simplify that, that's the ones place, fours place, 16s, 64, and 256 place, and then the quarters place, because 1 over 4 is 1/4. So that's what we really have to understand in order to convert anything to base 10. Because essentially, you're just figuring out what the place values represent, what number you have in them, and then multiplying and adding that. So I'll show you an example, right? So I have this example here where I have this number, which I'm going to call 101101.1 in base 2. And the reason we do that is because technically we can't call it 100, 1101 since it's in a different 0.1 in a different base. So we technically have to call it 101101.1 in base 2. So if I were to try and convert this into base 10, then I would have to use this method of using what the place values represent in order to do it. So what do these place values represent? Well, let's see. So here I have the 2 to the power of zeros place. Because remember, in base x, this is the x to the power of zeros place, or the 2 to the power of zeros place in base 2. This next place value is the 2 to the power of 1's place. This one's the 2 to the power of 2's place, 2 to the power of 3, 4, and then 5's place, right? 2 to the power of 4, and 2 to the power of 5's place. And then this decimal point, after the decimal point, it represents the 2 to the power of negative 1's place. So if we simplify these exponents and figure out what that's equal to, well, we have the 1's place, the 2's place, 4, 8, 16, 32's place, and then this one is the 0.5's place because 2 to the power of negative 1 is 0.5. So that's what these place values represent in base 2. Well, how does this help us? Well, it's really simple from here, actually, if you can understand this. In order to convert from base 2 then to base 10, you just have to figure out how many of each place value you have and add it together like you would in base 10. For example, this number in base 10 represents 1 10,000, 1 times 10,000, plus 2 times 1,000, because you have 2 in the 1,000th place. So you have 2 thousands, then plus 3 times 100, because you have 3 in the 100th place, and so on until you get to plus 6 times 0.1. So you can actually do the same thing in different bases. In base 2 now, if I figure out what this represents, well, we have 1 in the 32's place, so that's 132 plus, and then we have a 0 in the 16th place, so I won't write that one. Then we have a 1 in the 8th place, so we have 1 8, or plus 1 times 8. And then we have a 1 in the 4's place, we have 1 4, so 1 times 4. We have a 0 in the 2's place, and then we have a 1 in the 1's place, so we have 1 1. And then, oops, that was a 7. 1 1, okay. And then plus, and then we also have a 1 in the 0.5's place. So we have 1 times 0.5, right? And if we evaluate this all out, we end up with 32 plus 8 plus 4 plus 1 plus 0.5. And when you simplify that all out, that leaves you with 45.5. So 45.5 in base 10 is what equals this number 101101.1 in base 2. Specifically, this number in base 2 equals 45.5 in base 10. And this is how you convert from base to base. In any base, you figure out what the place values represent, like you could in base 10, and then you multiply the values in those place values, which could be 1, 2, 3, 4, 5, 6, 7, 8, and 9. If we get to bases above 10, then they'd be above that. And then you add those together in order to get your value in base 10. All right, so now I have a review question. If you'd like to try it, I'll give you a few seconds to pause the video and then I'll explain how to find the answer. So the correct answer to this question was 113. So it's asking us, what is 423 in base 5 expressed in base 10? So in order to do this, we have to use our method where we figure out what each place value represents and then use those place values and the numbers in them to add together and multiply in order to get our value into base 10. So let me write out the number 423 in base 5. Now remember, in base x, then the place values will be x to the 0, x to the 1, to the 2, to the 3, and so on, starting with this place value here, right? In every single base, this is actually the ones place. In any base, this will be the ones place because this is the x to the zeros place in base x. And any number to the power of 0 is 1. So we always start with the ones place. And if you're wondering, the decimal point would be here, even though we don't have a decimal. So this is why this is the ones place. Okay, so in base 5, this represents the 5 to the power of zeros place, which I mentioned as the ones place because 5 to the power of 0 is 1. All right, so our next place value will be the 5 to the power of ones place because we're in base 5, so everything is 5 to the power of something. And 5 to the power of 1 equals 5, so now this is the 5's place. All right, now this next place value is the 5 to the power of 2's place, right? So that's 25, so this is the 25's place in base 5. So now that we know the values of our place values for base 5, specifically for this number, we can use the numbers in those place values to calculate what our value in base 10 is. So what we have to do is figure out, okay, well, we have 4 in the 25's place, so therefore we have 4 25's in this number. So it's 4 times 25 plus, okay, well, how many 5's do we have? Well, we have 2 in the 5's place, so therefore we have 2 5's in this number, or 2 times 5, and then plus, and now we have 3 in the ones place, or we have 3 1's in this number. So 3 times 1, right? And now we have 4 times 25 plus 2 times 5 plus 3 times 1. 4 times 25 is 100. 2 times 5 is 10. 3 times 1 is 3. So there we have 100 plus 10 plus 3. And if you simplify that out, that's 113 in base 10. All right, so next we're going to be talking about converting from base 10. Because we already learned how to convert from some base to base 10. Now we're converting from base 10 to some base. And the reason why I taught you to convert to base 10 first is because in order to convert from base 10, you kind of have to think about how you convert to base 10 in the first place. Because it's basically the opposite method that you use to convert from base 10 then. So when you convert to base 10, it's always going to be the sum of some amount of different powers of the base number, which sounds confusing, but let me use an example. So remember the last example, that's what I'll use, where we converted 4, 3, 2 in base 5 to base 10, right? So I said it's always the sum of some amount of different powers of the base number. Well, different powers of the base number, which is 5, so different powers would be 5 to the 2, 5 to the 1, and 5 to the 0, for example. And so the result was 4 times 5 to the 2, because we had a 4 in the 5 to the 2's place, or the 25's place, plus 3 times 5 to the 1, because we had a 3 in the 5 to the 1's place, and then we had a plus 2 times 5 to the 0, because we had 2 in the 5 to the 0's place. And this is what I mean by it's always the sum of some amount of different powers of the base number. These are different powers of the base number. These are some amount of different powers of the base number. So we have 4 5 to the 2's, 3 5 to the 1's, 2 to the 5 to the 0's, and then it's the sum of all of those. Now, why am I telling you this? Because basically you have to reverse that when you convert to base, or from base 10 to some base. So to convert from base 10 then, you need to subtract a multiple of the highest powers possible that the base 10 number is greater than repeatedly until you are left with 0. Now, that's really confusing because it's hard to explain this in words. So I thought I would explain it through a few examples. So here I'm going to be converting 60 in base 10 to some number in base 3, and then I'll convert 22 in base 10 to some number in base 2. So if we look at our definition of how to convert from base 10, so you subtract a multiple of the highest power possible that the base 10 number is greater than repeatedly until you're left with 0. And then I'll add a comma here because you do that then repeatedly until you're left with 0. Okay, so we need to find the highest power possible that the base 10 number is greater than. So the highest power of base, or the highest power of 3 that this base 10 number, 60, is divisible by. Okay, well, so powers of 3. Let's see. We have 3 to the power of 0. There's 3 to the power of 1, 3 to the 2, 3 to the 3, 3 to the 4, and I'll stop listing them out as right there. So these different powers, when you actually multiply it out, are 1, 3, 9, 27, and 81. So these are different powers of our base number that we're converting to, 3, right? So we need to find the highest power possible of 3 that the base 10 number is greater than. Okay, well, so our base 10 number is 60. So the highest power here that we have that 60 is greater than is 27. Okay, and you need to subtract a multiple of that highest power until you're left with 0. And this is where it gets a little bit confusing to explain in words. So I'm just going to show you what I'm doing. So how many times does 27, the highest power of 3, the base that we're converting into, how many times does 27 go into 60? Well, 60 minus 27 is 33, and 33 minus 27 is going to give you 6. So 27 times 2 is 54, right? So 27 goes into 60 2 times, because 27 times 2 is 54. So now what we need to do is subtract 54 from 60, right? And since we did 2 times, this is where it gets confusing. Since it goes into 2 times, your base 3 number is going to start with a 2. Okay, so now our remaining number is 6. Okay, so let's look at our next highest power of 3, because 27 doesn't go into 6 anymore, obviously. We had 27 go into 60, the maximum amount of times. So now we have to move down to our next highest power of 3. So our next highest power of 3 is 9. How many times does 9 go into 6? Well, 6 isn't divisible by 9 at all. 9 goes into 6 0 times. So therefore, since we can do 6 minus 9 times 0, since 9 goes into 0 times, then 0 is going to be our next number in our base 3 number. So it starts with 2, 0. Okay, and that's still equal to 6, because 9 times 0 is 0, and it's not divisible. Okay, so now we keep dividing, right? So now we have 6, and we move to our next highest power of 3, which is 3. Okay, so how many times does 3 go into 6? Well, 6 divided by 3 is 2, and specifically 2 times 3 is 6, right? So 6 minus 3 times 2, because it goes into it 2 times, will equal 0, right? Because 3 times 2 is 6. And since 3 goes into it 2 times, our next number in this base 3 number is going to be 2. All right, and that's 0 left. And we have to keep going until we reach the ones place. I'll explain this in a sec, but basically you want to repeat this process until you get all the way down to 1. And we haven't gotten to 1 yet. So how many times does 1 go into 0? Well, that's pretty simple. 0 isn't divisible by 1. It goes into it 0 times. And since it goes into it 0 times, our next number in our base 3 number will be 0. All right, and now that we've reached 1, we can stop here. So in base 3, this is going to be 2020, or 2020. And if we think about what we did, and I'm going to reverse it by converting this back to base 10 to show you exactly what we did so it makes sense. We just took the place values and basically put them into the correct place values by figuring out how many numbers or how much should be in each place value, right? So in base 3, this is the ones place, this is the threes place, this is the nines place because it's 3 to the power of 2, and this is the 27s place because 3 to the power of 3. So this number in base 3 represents you have 2 27s, and you have 0 9s, you have 2 3s, and you have 0 1s. And if you converted this back to base 10, this gives you 54 plus 6, which is 60. So you're basically doing the exact opposite thing that you did to convert to base 10 when you convert from base 10 back to another base. All right, so I'll do one more example just to make sure it's in your head. If you're converting 22 in base 10 to base 2, you do the exact same thing. So let's list out our powers of 2. So powers of 2 are 1, then you have 2 to the power of 1, which is 2, 2 to the power, 2 to the power of 2, which is 4, 2 to the power of 3, which is 8, 2 to the power of 4, which is 16, and 2 to the power of 5, which is 32. And you can stop here, 2 to the power of 5, because you know that 32 is going to be higher than 22. And you need to find the highest power of the base number that you're converting to, that your base 10 number is divisible by. So 22 is divisible by 16, 8, 4, 2, and 1, but it's not divisible by 32, right? 32 is higher than base 2, than 22. So the highest power of 2 that 22 is divisible by is 16. So now we need to figure out how many times does 16 go into 22. Well, 16 goes into 22 only one time, right? So 22 minus 16 times 1 is going to give you 6, because 16 times 1 is 16, and 22 minus 16 is 6. So therefore, since it's 16 times 1, since it goes into it one time, then our base 2 number is going to start with a 1. All right, so next we have 6 remaining. So now we need to go to our next highest base 2, or power of 2, because we know 16 won't go into 6 anymore. So our next highest one is 8. How many times does 8 go into 6? Well, 8 goes into 6 0 times, or 6 minus 8 times 0. Oops, that's just 80. 6 minus 8 times 0 equals 6, right? Because 8 times 0 is 0. And since it's 0 here, 8 times 0, then we put 0 as our next base 2 number, because it goes into it 0 times. All right, so far our number is 1, 0, and we still have 6 remaining. We haven't gone to this ones place yet, so we have to keep going. All right, so our next highest power of 2 is 4 then. So what we have to do is see how many times does 4 go into 6? Well, it's just one time, because 6 minus 4 is 2. So 6 minus 4 times 1, since it's one time, equals 2. So now we have 2 remaining, right? And since it goes into it one time, 4 goes into one time, in the 4th place, we're going to put a 1. All right, so now we have 2 remaining. Now we go to our next highest power of 2, which is 2. How many times does 2 go into 2? Well, that one's really simple. It's just once. 2 minus 2 times 1, since it's one time, equals 0. And since we did it one time, 2 goes into 2 one time, our next number in this base 1 number, or base 2 number, will be 1. All right, and then we have to keep going. Even though we have 0 left, we have to keep going until we get to this ones place. So now we do it one more time to finish off in the ones place. So how many times does 1 go into 0? Well, any number goes into 0 0 times, right? So 0 minus 1 times 0 equals 0. And since it goes into it 0 times, then we put a 0 in the ones place of this base 2 number. And so our result, 22 base 10 equals 10110 in base 2. And finally, I have a review question about converting from base 10. If you'd like to try it, I'll give you a few seconds to pause the video, and then I'll explain the answer. So the correct answer to this question was 1123. So the question is, what is 91 in base 10 expressed in base 4? So remember, when we're converting from base 10 to another base, we need to figure out the highest power of the base number that we're converting to that our base 10 number is divisible by. So let me write out my base 10 number, which is 91. All right, so we need to figure out the highest power of our base number we're converting to, which is 4, that 91 is divisible by. So let's start listing out our powers of 4. So first we have 1, which is 4 to the power of 0, because you always start with 1. Then our next one is 4 to the power of 1, which is 4. 4 to the power of 2, which is 16. 4 to the power of 3, which is 64. And then 4 to the power of 4, which is 256. And I know we can stop at 256 because 91 is not going to be divisible by 256 at all with the remainder. 256 is greater than 91, which means we can stop here. Okay, so the highest power of 4 then, that 91 is somewhat divisible by, is 64, because 64 can go into 91 at least once. So now it's our job to go through the powers of 4 and figure out how many times each of them goes into 91, or whatever we subtract and have as our remainder from 91 when we use our other powers of 4. So first, how many times does 64 go into 91? Well, the answer is going to be once, because if we subtract 64, or just 164, which is why I'm doing 64 times 1 here, from 91, that's going to leave us with 27. And since 27 is less than 64, we know 64 only goes into 91 once. All right, and now since 64 goes into 91 once, then in our 64th place in this base 4 number, we put a 1. All right, so now we have 27 remaining, right? So now we need to move to our next highest power of 4 that we haven't used, which is 16. So how many times does 16 go into this subtraction number, or remainder, right? 27. So how many times does 16 go into 27? It goes into it once, because if we subtract 16 once, or just 116, which is why I'm doing 16 times 1, from 27, then we're going to be left with 11. And since 11 is less than 16, we know 16 goes into 27 once. Now, since 16 goes into 27 once, then in our 16th place, we're going to put a 1 in our base 4 number. All right, so now we have 11 left. So now we have to move to our next highest power of 4, which is just 4. Figure out how many times does 4 go into 11. And it's going to go into it twice. So if we subtract 4 times 2, because it goes into it twice, then that leaves us with 3, because 4 times 2 is 8, 11 minus 8 is 3. Right? And since 3 is less than 4, we know 4 only goes into 11 twice. Now, since 4 goes into 11 twice, in our 4th place, we put a 2. And now finally we have 3, and we're down to the 1's place, which is when we can stop after we do this. So since we have 3 here, and we need to figure out how many times does 1 go into 3, well, that's pretty simple. It's just 1 time. 1 goes into any number, whatever that number is, times. So it goes into 27 times. It'll go into 0 times. So it goes into 3 times. So 3 minus 1 times 3 is going to give us 0, right? And since it goes into it 3 times, in the 1's place of our base 4 number, we put a 3. So now our result is 1, 1, 2, 3 in base 4. And just as a side note, if you do have a decimal when you're converting, say I had 91.5, right? Say 91.5. And say you're left with the 0.5 at the end because you do the 1's place and 3 goes in, and 1 goes into 3.5 only 3 times, you'd be left with 0.5 at the end. You would actually have to keep going after this if you haven't reached 0, right? So you'd have to go to next to the power below this, which is 4 to the negative 1, or 0.25, and figure out how many times 0.25 goes into 0.5, which would be 2 times, which is why if this number was 91.5 in base 10, we'd have 1123.2, because you have 2 0.5s that go into the remaining number, which is 0.5. So that's just a side note. If you are converting like this and converting from base 10, if when you get to the 1's place, you still have a remainder that's not 0, you have to keep going after that. But if you do have a remainder that's 0 before that, or when you get there, then you can stop. All right, now just to quickly review what we've learned this lesson. So first we started with explaining what bases are, and we do this in 2 separate ways. So the first way is we said a base is a number that represents how many 1-digit numbers there are in a number system. And so I was talking about how everything I've taught in any video has been in base 10. So we looked at how bases work in base 10 specifically. So when you have a number in base 10, all your place values will be different powers of 10. So the 1's place is the 1's place because 1 is 10 to the power of 0. The 10th place is the 10's place because 10 is 10 to the power of 1. The 100th place would be the 100th place because 100 is 10 to the power of 2, and so on. And even the 1/10th place, or the 10th place, is the 10th place because it's 10 to the power of negative 1. Now, this is what changes from different base to base. Since we're in base 10, everything is powers of 10. But if we're in a different base, say base 2, then all our place values would have different powers of 2. So we'd still have a 1's place because 1 is 2 to the power of 0. But next we'd have a 2's place because 2 is 2 to the power of 1. And then a 4's place because 4 is 2 to the power of 2, and so on. And even here we'd have a 1/2's place because 1/2 is 2 to the power of negative 1. Then the other way I explained bases is by talking about how you count in different bases, and the fact that a base represents how many 1-digit numbers there are in a number system. So we talked about counting in base 10, where when you get to 9, then you move to the next number, which has to be 2 digits because there's no 1-digit number greater than 9. And when you get to 99, you move to 100 because there's no 2-digit number greater than 99. And the reason why is because in base 10, you only have 10 1-digit numbers, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now, this is what changes in different bases. So an example, in base 5, you only have 5 one-digit numbers, which are 0, 1, 2, 3, and 4. So just like when you get to 9 in base 10, how you move on to two-digit numbers, when you get to 4 in base 5, you move on to two-digit numbers. So in base 5, instead of counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, you would count 0, 1, 2, 3, 4, 10. And when you got to 44, since there's no one-digit number higher than 4 that a two-digit number can be made out of, you have to go to 3 digits, or you have to go to 100. And then we talked about converting to base 10, where learning the place value explanation of what bases is will help you a little bit more. So in any base, or base x, the place values of a number starting with the ones place will be x to the 0, then x to the 1, to the 2, to the 3, to the 4, and past the decimal point, it goes negative. So x to the -1, 2, 3, 4, and -1, -2, -3, and -4, and so on. All right, and then we did an example where we converted 101101.1 in base 2 to base 10 by finding the values of each of these place values, so the 1s, 2s, 4, 8, 16, 32s, and 0.5's place, and figure out how many numbers we have in those place values specifically to convert it to base 10. And then we did a review question where we converted 423 in base 10 to 113, or in base 5 to 113 in base 10. Then after that, we talked about converting from base 10, which is essentially the opposite of converting to base 10, which is why I taught you that first. And what you do is you find the highest power of the base that you're converting into that the base 10 number is divisible by, and then find all the lower powers than that and keep subtracting until you have 0. And basically the amount of times you can subtract each of those place value numbers, or those powers, is what number goes in that place value when you convert it to base, or whatever base you're converting to. So then we did 2 examples where we converted 60 from base 10 into base 3 and 22 in base 10 to base 2. And finally, after that, we did a review question where we converted 91 in base 10 to base 4, which is 1123. All right, so that's all I have for today's lesson. I hope it was helpful. We're going to continue with bases next time because I actually didn't get through as much with bases as I wanted to in a shorter time period, because bases actually have a lot to them and are pretty confusing. So yeah, I hope this was helpful, and I'll see you next time then.